Now, for example, we have two numbers. For example, we have two numbers, 313 and 156. And we want to find greatest common divisor. Greatest common divisor, it's denoted by greatest common divisor. I think you know what is greatest common divisor for two integers. And also you may know how to find it. Basically, in secondary school, to find it, we have two ways. And one of this way, it's called Euclidean algorithm. And Euclidean algorithm, it's based on the idea that any integer can be represented as integer a, can be represented when integer a we divide by positive integer b, it can be represented as b times q plus remainder, and the remainder it's greater or equal 0 and less than b. So by this Euclidean algorithm, we can find greatest common divisor, and let's do it. Step 1, 330, if we will divide by 156, we can represent it as 156 times 2 plus 18. So 330 we divided by 156, and we represented it in this view. Okay. Now, next step here is 356 to divide by remainder in the same way. This is Euclidean algorithm. But today, we also will discuss about extended Euclidean algorithm. And extended Euclidean algorithm, it allows to represent greatest common divisor as a linear combination of integers. And that's why in this first step, from here, I should solve this equality for 18. From here, 18, it equals 330 minus 356 times 2. Okay. Next step, this is step 1. Next step is 356. We should divide by remainder, by 18. And if we will divide 356, it equals 18 times 8 plus 12. Okay. Now, in the same way, from this equality, I will define 12. And 12 from here, it equals 156 minus 18 times 18. 18 times 8. Okay. Please help me now to find what will be next step.
Divide 18.
Now, what we should divide? 18 now we will divide by 12. And 18 equals 12 times 1 plus 6. From here, in the same way, 6 equals 18 minus 12 times 1. And finally,
Isn't this basically long division?
yes, it's division, David.
Long division, okay.
Yes, yes. Now, from here, 12, we should divide by 6. And 12, if we will divide by 6, it's going to be 6 times 2 plus 0. And this number, last remainder, last non-zero remainder, it's greatest common divisor of numbers, of given numbers. Okay. Now, next step now is how to represent greatest common divisor, and this is 6. How represent 6 as a linear combination of given numbers. Given numbers, I mean 330 and 156. For this, here, now look to right side, and we will now go upward. So we have here 6 equals, I will just rewrite it, 6 equals 18 minus 12 times 1, it equals, and now 12, I will replace by 12 from the expression above. So in this expression, 12 equals 156 minus 18 times a, and I will represent it. I will replace 12 by this expression. So we have 18 minus 156 minus 18 times 8. I hope you are writing it down. Let me continue. And I think you guess next step. But now let's simplify it. And if we will simplify it, so I hope you guess next step there will be 18. We will replace by expression, by first expression. But I strongly recommend before replacing 18 by equal expression to simplify this expression. And simplify, I mean, here we have 18 minus 18 times 9, and it's going to be 18 times 9 minus 156. Minus 156. Please look carefully if any questions. No questions? Okay. No. Now 18 we should replace by 330 minus 156 times 2. And now we have here 330 330 minus, look very critically, 2 times 9 minus 156. And if we will simplify this expression, it's going to be 9 times 330 minus 10 times 156. And this is a linear combination. To be more exact, what is linear combination?
I think it's 19, not 10.
Yeah, it's 19.
Oh, yes, it's 19. Thank you. To be more exact, what we mean linear combination? If we have two numbers, A and B, linear combination of these numbers, we called A times C plus B times T. So when we say that greatest common divisor, it can be represented as linear combinations of A and B. I mean that greatest common divisor, it can be represented as A times S plus B times T. And here, S and T, they are integers. Of course, they can be positive, negative, or zero. They are both integers. And to get exactly the same expression, I can represent it as a 9. I can represent it as 330 times 9 plus 156 times negative 19. Any questions?
Yeah, I have a question about this. So what do we use this in? So what is it used for? What do we need it for? Like, when do we need to use it?
Well, okay, Luca, we will see it very soon. We will see it
Okay.
very soon.
Great.
Okay. Okay. Let's continue. So, you know what is prime number, but do you know what is relatively prime numbers?
Their common divisor is 1.
Yes, when common divisor is 1. For instance, 9 and 8, they are relatively prime numbers. Because common divisor, they have only one divisor, and this is 1. Okay, good. So now we know what is relatively prime numbers. Now, let's now suppose that A and B, A and B, they are relatively prime numbers. What do you think? If I will write down that, if I claim that A and B, I can represent one as A times S plus B times T equals 1. True or false? So it's given that greatest common divisor A and B, it's 1. What do
True.
you think? It's true or false?
True.
It's true. And why? Because we know that greatest common divisor we can represent as linear combination of A and B, and that's why, since we have that they are relatively prime numbers, greatest common divisor is 1, and always we can represent 1 as a linear combination of relatively prime numbers. Let me recall that A, S, T, they are integers, positive or negative. Okay, now let's discuss example. And this example is two numbers. We have two numbers, 360 and 43. And we want to represent 1 as linear combination of these numbers. You can check that they are relatively prime numbers. It's easy to check because 43 it's prime number. 660 it's not divisible by 43, and hence they are relatively prime numbers. But before starting this to represent as linear combination, let me ask. So we agreed that when A and B are relatively prime numbers, 1 we can represent as linear combination of A and B. Okay, but now my question now is, can I claim that if A and B, they are relatively prime numbers, if A and B, they are relatively prime numbers, can I claim that there exists as integer such that A times S congruent 1 mod B? So we agreed, this is our firm agreement, that if A and B are relatively prime numbers, we can represent as linear combination. We can represent as linear combination. It means that there exist S and T integers such that this equality is true. This equality is true. I mean this equality. This equality is true. There exist S and T. Now my question is, can I claim that if A and B, they are relatively prime numbers, there exists S from Z, and by Z we denoted integers, set of integers. There exists S integers such that A times S congruent 1 modulo B.
Yes,
I
I
get-
think yes.
Yes, I think so as well.
Okay, thank you. And why? Could you explain?
Yes, I
Because-
can. So we can write it in a form that AS
Very good, Katie.
minus 1.
I got. So very good. So this I can represent it A times S by definition of congruence. I can represent it A times S A times S equals 1 plus B times K. Now from here, A times S equals, not equals, but now I will move B times K to left side, and we have A times S plus B times minus K equals 1. And now I can denote minus K by T, and we have the same expression. Okay, it's good feeling when you remember what we discussed previous class. And for this, it's necessary to review before class and after class to review this material. Okay, now let me continue. And now my goal is to represent 1 as linear combination of numbers. So represent as linear combinations, it means there exist such S and T that 360 times S plus 43 times T equals 1. Okay, any idea how can we do it? By Euclidean algorithm.
Yes, same way.
By extended Euclidean algorithm. So we can first divide 660 by 43, and it's going to be 43 times 15 plus 15. Okay, now please me, what will be next step? Next step, or this step, it does not matter. It's to define from here what is 15. And 15 from here, 15, it's 360 minus 43 times 15. 43 times 15. Okay, and now, a next step now, what is next step now?
43 equals 2 times 15 plus 30.
Very good, Salome. 43 equals 15 times 2 plus 15 times 2 plus 13. And also I will define 13. 13 equals 43 times 15 times 2. And now what is next step? Next step is 15 to divide by 13. So 15 equals 13 times 1 plus 2. And again, 2 equals 15 times 15 minus 13 times 1. And what is next step?
Divide 13 by 2.
Yes, 13 divided by 2, and 13 equals 6 times 2 plus 1. And from here, 1 equals 13 minus 6 times 2. And finally, 6, if we will divide 6 by 1, it equals 6 times 1 plus 0. And this number 1, it's last non-zero remainder. So this is greatest common divisor, and we knew it. We decided it without Euclidean algorithm. Okay. Now, what is now next step? Next step now is to go upward. Go upward. We have it 1 equals 13 minus 6 times 2. And let me to continue here. Let me to continue here. And it's equals. Now we are going backward. Please help me what to write here.
We should replace 2 by 15 minus 13
Very
times 1.
good, very good. So we should replace 2, it equals 13 minus minus 6 times 15 minus 13 times 1. Okay. It's going to be, please mute your microphone. And it equals, please help me.
We should replace 13.
Yes, no.
We should simplify.
Yes, first of all, we should simplify. It's very important, Salome. I emphasized it, and I would like to emphasize again that before replacing, it's very important. It's very important because we get more simple expression. It's very important to simplify before replacing. So
Yes,
if we will replace, it's going to be
7 times
13 times 7
yes, and minus 6 times 15.
minus 6 times 15. Okay. Now we will replace it now. We will replace it now 13, and it's going to be 43 minus 15 times 2 times 7 minus 6 times 15. And now from here, I will write here. Okay. And what we have. And so now finally we have that if we will simplify it, then we will replace. Finally, I have here answer, and finally we have that. Finally, we have that 1 equals 43 times 43 times 307 plus 40 plus 660 times minus 20. By the way, if you want to check, do you have correct answer or not, you can just take calculator and complete. Multiply 43 by 307, then subtract, and you should get 1. Any questions?
What is the purpose of this? What is this actually used for?
Okay, very good question, very good question. Also look ahead, the same question, David, and we will see it very soon. And now what it means. By this method, we can find this number S, and this number is called inverse of A modulo B. And to give more exact definition, I will write down it that when A times S congruent 1 modulo n, this number S called inverse of number A modulo n. And finding this number, this is key of RSA, crypto system. To decrypt, and this is topic of our next class. Next week, we will discuss on the crypto system, and this is key to find this number. And key here is that it's always possible to find this number, inverse of A modulo n. It's always possible when these numbers A and n, they are relatively prime. Common divisor, greatest common divisor of numbers A and n, this is 1. Okay, so now let's now formulate our previous problem in a different view, and to find S integer such that 43 times S congruent 1 modulo 360. So when we need to find such S, first of all, we should define, is it possible or not? And in this case, it's possible because 43 and 360, they are relatively prime. And how to find it? And we can see here that it's represented. I hope you wrote down it, and 43 times 307, it congruent 1 modulo 660. So this inverse of 43 modulo S, this is this number 307. So S inverse of 43, this is 307. And we need it for decryption in RSA crypto system. Okay, so please make sure that this is correct. This is correct because, why it's correct? Because we already represented one as linear combination of 43 and 360. And we represented it as 43 times 307 plus 660 times minus 20. And because of this, I can write this congruence. And I can define from here S. S is called inverse of 43. Please, if any questions.
I still do not understand this. 1 mod 660 would be the remainder of 1 after dividing by 660. What remainder would there be? 1 is less than 660.
660, David, it's not remainder. 360, it's not remainder.
I know
This,
that.
This, it just means this congruence. Okay, let me write down what it means, this congruence. This congruence, it means that 43 times 307 minus 1, this number is divisible by 360. And what it means it's divisible by 360? It's divisible by 360. It means that we can represent it as k times 360. And from here, if I move it here to right side, we have 43 times 307 plus 360 times minus k equals 1. And minus k in this particular case is just 20. Not minus k, but k, it's 20. Minus k, it will be minus 20. David, do you have any extra question?
No. Okay, 6.
No. Now let's do now 4 small numbers, and I think it will be more clear. So now we need now to find, just a minute. Now we need to find linear combination of numbers 3 and 14, which will be equal 1. So we need to find such s and t such that 3 times t plus 3 times s plus 40 times t equals 1. In other words, we can formulate our problem like this. Find s such that 3 times s congruent 1 modulo 40. We need to find s. To find s, we will use Euclidean algorithm, and 40 we can represent as 13 times 3 plus 1. Do you agree?
Yes.
And from here, we can write down that 3 times minus 13 plus 40 times 1 equals 1. Of course, I can write this in different views. It's natural here is to write that 40 minus 13 times 3 equals 1. But I wrote down in this view because to be this expression, the same view, in this view. Because now, it's easy now to find s. What will be s? Here. If we will compare to this expression, we this expression and this expression, if we will compare these two expressions, it's easy to find that what is S? S is negative 13.
Minus
S is negative 13 because if we compare, we have here 3, 3, 40, 40, T is 1, and S is minus 13. So I can write down that I found S such that 3 times minus 13 congruent. 1.
Okay, I'm going to ask this once again. What chapter is this in the book? Which chapter is this on in the book?
Each chapter is David. In the module I uploaded, in the module, I think it's module 9, I uploaded this chapter. Each chapter 9-4, 8-4.
Okay.
Yes, 8-4. So I wrote down it. But in the crypto system, there is required to find inverse, not any inverse, but positive inverse. So if we want to decrypt something using RSA crypto system, it's not good that we got here negative number. We need positive number. And any idea how to find positive inverse? So I hope we all agree that minus 13, this is inverse of 3 modulo 40. Why? Because here we have representation 3 times negative 13 plus 40 times 1 equals 1. But my question is it possible to find S, positive S, which satisfies this equality? This equality, 3 times S plus 40 times T equals 1. We need S positive. I found negative S. Negative S is good in modular arithmetic, in number theory, but it's not good when we need to decrypt using RSA crypto system. We need positive inverse. And now my question is, how to find what will be positive inverse? So we have here 300 minus 13. This is my last question.
27.
What, Jacob?
I think it's 27 because 3 times
Oh, it's
27
great. It's great,
minus 40
Jacob.
times 2.
Great. It's 27. It's 27. And I will show now why. Because 300 minus 13 plus 300 minus 13 plus 401 equals 1. We have this. Now, what happened if I will add if I will add 340 and then subtract? I think you agree that I can add 340 and subtract. So now if I will factor out from here 3, we have 3 times 40 minus 13, it's 27, and minus not minus, but I will write down here, plus 40 times minus 2 equals 1. So in the problems, if you will get inverse of modulo negative number, to get positive, you need just to add this number, modulo 40. And here is why. Because it's represented in this view, 1, our common divisor. Then I can add 340 and subtract, and I have this expression. And from this expression, we can conclude that 327 congruent 1 modulo 40. Please ask any questions, and now at the same time, I will publish your quiz. So, David, our textbooks are on the home page. There are 2 textbooks. Now we
have the textbook. I just
use
wanted to know
first
the
one.
chapter. Okay.
Now we used first one, and also in combinatorics we will use second one. It's on the home page.
I know that.
Okay, and also you can find a particular chapter in the correspondence modules. So it's published, quiz 9.